Okay, so the force we're looking for is actually a force that's acting on box B. Okay, but there's a problem. I don't know very much about box B. How many forces are acting on box B? Well, within the movement plane. 2. Friction, of which I have no idea. They didn't tell me what the force of friction is on box B. I have no way to calculate it. And they want this force. Well, all I can calculate about box B is the net force. That's it. And not that that's not useful, but it doesn't get me anywhere because I don't have anything else about box B. So, here's what I have to understand. This is the only Newton's third law part of this question. Is there an action-reaction pair for the force of A on B? Is there another force in this situation that is equal to but opposite the force of A on B?
Force of B on A.
The force of B on A, which I would use box A to get. Box A is better because I know all of the forces acting on box A. I know it's being pulled this way by 600 newtons. I know that the force of friction is 200 newtons. And I know that there's also the force of B on A, which is the action-reaction pair for the force that I'm looking for. Now it's a Newton's second law question. Okay, actually it already was. Okay, as soon as we realize those two forces are equal, after that, it's a Newton's second law question. Okay, so I know this is 75 kilograms. So right away I'm going to get the net force on box A, so mass times acceleration. Oh shoot, I closed my calculator. What's 75 times 1.2? 90? All right, so the net force is 90 newtons in a forward direction. Okay, we also know that for box B, F net is the force of friction plus the applied force at 600 newtons, okay, plus the force of B on A. So if I want to isolate the force of B on A, okay, I'm simply going to go F net minus the force of friction minus the force of B on A. Okay, sorry, the applied force. I'm looking for the force of B on A. Okay, minus the applied force, okay, and that will give me the force of B on A. Okay, so when I plug in my numbers there, that's going to be 90 minus 600 minus negative 200. Okay, I have to keep in mind that friction is acting backwards. Okay, and I want to get a negative number here. Would you agree? Right, because the force of B on A is backwards. All right, so when I punch all that in, I've got 90 minus 600 minus negative 200. Okay, so 310 newtons is the force of B on A. So the force of A on B is, to two significant digits, 3.1 times 10 to the 2 newtons forward. Okay, force of A on B would be in a forward direction. Okay, you won't see anything more difficult than that in terms of a Newton's third law question on your exam. Okay, what else? System question, yep. Oh, I had a 2-box question right there. I missed it. Okay. Did you guys get to this one in class? You did? Okay. Let's try a different one. Let's try. Okay, so these two masses are hung over a frictionless vertical pulley. I want the acceleration of the 3 kilogram mass. What's the big trick with all systems questions? The acceleration is calculated by using the total mass of the system. All parts of the system have the same acceleration. Okay, so our forces here are the force of gravity here, okay, m times g, so 3 times 9.81, 27 point something, right? 29.43. Okay, 29.43, okay, and then this one's going to be like 14 point something, right? Oh, not 15, 1.5 times 9.81. Okay, so 14.715. Newtons. Okay, at this point, I simplify that diagram and I say that there is 4.5 kilograms worth of mass being pulled this direction by 29.43 newtons, resisted this direction by 14.715 newtons. I calculate my net force, 29 minus 14, with all the decimals obviously. Okay, of course it is. That was stupid. Why did I punch that in? Okay, 14.715 newtons is my net force. Okay, and now that I know that, I can calculate the acceleration. F net divided by m. Okay, and it's just going to be 14.715. Okay, divided by 4.5 kilograms. Okay, so the acceleration of the system is going to be 3.3 meters per second. But it asked me for the 3 kilogram mass. So it's 3.3 meters per second squared down. I have to give a direction because it asked about a specific part of the system. Okay, questions on that one? All right, what else?
Coefficient of friction.
Coefficient of friction question. Okay. Okay. The vectors and coefficient of friction question. Okay, so in this question, I want the acceleration of the 8 kilogram box, knowing that it is being pulled with a 95 Newton force, angled 30 degrees above the horizontal. The box is not moving that direction, it is moving horizontally along the table. Okay. The key thing we have to realize for this one is that it's moving horizontally, not in that angled direction. So the first thing I want to do is draw my free body diagram and eliminate the angled force by finding its vertical and horizontal components. Okay, so I'm going to get rid of the 95. Once I've figured out how much of it is pulling horizontally, that would be the cos of 30 times 95. Okay, so 82.27. I'm just going to draw that arrow here. 82.27. Okay, and I want to find its vertical component as well, so that'll be the sine of, well, so it'll be 47.5 newtons. Okay, so now I can get rid of this angled force. Okay, and I'm simply going to move these other forces into place. Okay, what other forces do I need to put on there? Okay, those are the other forces acting on this box. Since the box isn't moving vertically, what do Fn, 47.5, and Fg add up to? Yeah, they add up to, yeah, 0, right? If I total them all, okay? They add up to 0. The forces up and the force down have to be equal but opposite. So this is m times g, so this is going to be 78.48 newtons. Okay? Now, because I was lifting this thing slightly, not enough to move it vertically, but I'm taking some of its weight off of the table with that angled force, that means normal force and gravity are not equal in this situation. Okay? Those two forces are only ever equal if something is sitting on a level surface with no other angled or vertical forces. Okay? It's actually less common than we think it is. Okay? There's almost always something else going on. Okay? So if I want to calculate the force of friction, do I need this number? I do. If I'm going to calculate the acceleration of this box, I need to know the force of friction. Okay, so I've got to calculate Fn. Well, if Fn, 47.5 and 78.48 add up to 0, then I should just subtract 47.5 from 78.48, right? That would mean the missing force. Okay, so do you guys remember this question from the assignment? Okay, you had to first find the angle, it was 51.1, and then you had to find the normal force, and so many of us just went mass times gravity. Okay, it's the same question. Okay, so Fn is going to be 78.48 minus 47.5. Okay, so the normal force is only 30.98 newtons. Can I find the force of friction now? Okay. Okay, so 3.4078. Okay, that's practically nothing, is it, compared to the forward force? All right, so now, can I calculate the net force? Yeah, I already know these forces all add up to 0, so I don't even have to factor them in. Okay, and I can just say that F net is 82.27 minus 3.4078. Okay, there's my net force. Divide that by my mass, which was 8. Okay, there's the acceleration of that box. 9.6. Oh, I mean, do we have two significant? We only had one significant digit. 10. No, 1 times 10 to the 1. I'll never do that on a test. That's silly. Okay, but it should have got around this number, 9.8, okay, 9.9.
If it's one decimal point, then technically you didn't even have to do friction because it went to, like, changed it enough.
Yeah.
Still went in.
If it was only the one significant digit, yeah. Okay, everybody with me there? Okay, it's very easy on a question like that to forget that normal force and gravity are not always equal. Okay, they're not equal on an inclined plane. They're not equal if you're pulling or pushing on the object. Okay, especially if there's any vertical component to that. Okay, that's probably the most common thing people forget on a question like that. Should you expect one like that? Well, it tests a lot of things. It's a good Newton's second law question. It's a good vector question. It's a good friction question. I like questions that test 3 things in one question. Makes the test shorter. Okay? So yeah, expect me to ask something like that. What else? Inclined plane? Oh, that's an energy question. I'll just make one up. Did you want it as an energy or a Newton question? Doesn't matter? Okay. Okay. This box is on a 25-degree incline. The coefficient of friction is 0.255. It is accelerating up the ramp at 1.2 meters per second squared. I want you to calculate the force pulling it up the ramp, the applied force. This is probably harder than what I would ask on an exam. First thing we have to do when we look at this question is decide what other forces are acting and which way do they go. Okay, F parallel always acts down the ramp, so anytime there's a ramp, there's F parallel. Okay, the trick is friction. The box is moving up the ramp, friction has to be down the ramp. It always opposes the motion. Okay, so now that I've got those on there, now I've got to put in my other little triangle here in order to get the numbers I need to calculate those forces. Okay, so this will be Fn, this will be Fg, and then this will be F parallel. And this angle is 25 degrees. Okay, so Fg is going to be m times g, so 12 times 9.81. So 117.72. I always miss a decimal, 0.72, right? Okay, newtons. All right, so I've got that side there being 117.72 newtons. Now I can get the other two sides. Fn will be the cos. What do I need Fn for? To get the force of friction. Okay, I need Fn if I'm going to get the force of friction here. Okay, so I'm going to go cos of 25 times that number. My normal force will be 106.69. Okay, so that I'll use to calculate friction, and I might as well calculate F parallel while I'm here. It's the opposite side, so the sine of 25 times 117. Okay, so that side's 49.75. Okay, so I've got one of those two forces. Now I can calculate the force of friction because I have mu and I have the normal force. So I'll simply put those together, 0.255 times 106.69. All right, so friction is 27.2 newtons. Okay, what's the other thing I could calculate that I could have calculated right from the beginning and didn't for whatever reason? Yeah, the net force. Yeah, I need the net force. Okay, so that's going to be mass times acceleration. Okay, so that'll be our 12 kilograms times 1.2. So 14.4 newtons. Okay, so F net on this ramp is going to be the applied force, which I don't know, plus the force of friction, plus F parallel. Okay, vector sum of all the forces involved. Okay, so when I want to find FA, FA will be F net minus F parallel minus the force of friction. And when I do that, I have to keep in mind that those two are down the ramp, but net force is up the ramp. So I'll have 14.4 minus negative 27.2 minus negative 45.75, or 49.75. Okay, so minus negative that number minus negative that number. Okay, so the applied force has to be 91 newtons up the ramp. Okay, and while that's a good question because it tests a bunch of different things, it's probably more than I would bother to test in one question on a unit exam. Okay, if I want to test coefficient of friction, I probably am going to do it somewhere other than an incline plane. Okay, all right. Anything else we want to work on or ask about? I did have a few questions about power. Okay, all you need to know about power is how it works. You will not be asked to do any calculating with it. Okay, the last time someone asked me this, they said, like, here's essentially what you're gonna have to be able to do. If I were to ask you, which hair dryer will dry your hair faster, a 1500 watt or a 1000 watt hair dryer, you would say the 1500 watt because it has more watts, which are the units for power. That you're not calculating anything, you just have to understand that power is how fast you do work, and the bigger the watts, the faster the work is done, okay, because it's joule per second. If you understand that, that's really all you need to know about power. Alex, you had a question?
Will you do another one of those box questions that have the rope in equal?
Okay, I've got one where there's no rope, but it's a 2-box question, how about that? Okay, give that one a try. Or did you guys get to that one on Friday?
Maybe not, I can't remember.
Okay, well, if you can't remember, then it's worth
I
doing.
wasn't there on Friday.
Oh, okay, that'd be why you can't remember.
Yeah, we did this. Yeah.
You did that one? Okay.
I think I was here at school.
Yeah.
Obviously.
Yeah, I wasn't here. I had the sub playing it. Don't have one in there either. Okay. All right, well, let's just make up another one here.
The rate of which work is done.
Joules per second. So it's like 8%.
Gate.
Okay, so we're looking for what's the force of box B on box A. Okay, there's a force acting directly on box A of 32 newtons. The force of friction acting on box B is 15 newtons. Okay, and the acceleration of the system is 0.85 meters per second squared forward, this direction being forward. Okay, that is also the direction the force acting on A is pushing. Okay, so I'm looking for the force of B on A. All right, so on this question here, okay, they want me to find the force of B on A, which is a force that is acting on box A. So what I want to do first is just have a look at box A and see what other forces are acting on it. I know there's this force. Okay. Since I'm told there's friction, there must be a force of friction acting on A, and there's the force I'm looking for, force of B on A. Do I have any way to calculate that force? Nope. So I can't find the force of B on A, but in this system, is there an action-reaction pair for it? The only reason B pushes on A is because A pushes on B. All right, let's look at box B and see if we can do better with box B then. Okay, ooh, box B has a lump in it. Okay, there's box B. Okay. The force pushing B forward is A, the action-reaction pair to the one I'm looking for. Okay? And they told me that B has a force of friction acting on it of 15 newtons. Okay? All right. Can I calculate the net force here?
Yeah.
I can, because I was told the acceleration and I know the masses. So, F net will be m times A, and F net will be force of friction plus the force of A on B. And I'm going to I have this number already, and I'm about to have this number. So yeah, I can use box B to get the thing I'm looking for, or rather, it's opposite. Okay, so we'll take 6 and multiply it by 0.85. Okay, so the net force on box B is 5.1 newtons. Okay, and F net minus the force of friction should equal the force of A on B. Everybody okay with what I did there? That's just the vector sum of all forces. Okay, so that's going to mean then, I'm going to take that 5.1 newtons forward and subtract negative 15, okay, and I'll get the force forward. All right, so I'm going to get 20.1 newtons as the force of A on B, and that will be forwards. So, what's the force of B on A? Yeah, well, or just, in fact, we only have, I did this again. Let's just say that that was 6.0, okay? Negative 20 newtons, okay? Or 20 newtons backwards would be the force that B exerts back on A. Okay, everybody with me there? Okay, what's the most common mistake you suppose people make in this question? They forget to make friction negative. That's the most common mistake in a question like that. They'll get everything right up to that point, which is the bulk of the question, but then they'll make that little mistake. They'll forget to make friction backwards. Okay? And as a result, they get a really weird number. All right, anything else?
Do you want to work energy theory question?
A work energy theorem question? And what were you going to ask? Same thing? Okay. Had a work energy theory question. Go. Had a work energy theory. There it is. Okay, I would like you to find the final height of the 6 kilogram box. Okay, it is starting at the bottom of the ramp, moving at 2 meters per second. Later, it is at the top of the ramp, moving at 5.5 meters per second. Okay, and the force being applied to it is 15.96 newtons. All right, so unit 3 is the shortest of the 4 units. Okay, like it's usually 3 weeks and we're done. All right, so like by the end of next week, I'll probably be telling you when your unit exam is. Okay, like it's really literally that short. Okay, the good news is it's also usually the easiest unit. Okay, it does still build on a little bit of Newton's second law stuff, but it just applies it to things moving in a circle rather than things going up hills or ramps or whatever. Okay? So, first off, we have to understand what circular motion is. This is my dual-purpose ghetto physics demonstrating tool. Okay? So if something is moving like this, would that be circular motion? Okay. What makes it go in a circle?
Inertia?
Actually, its inertia would make it go in a straight line.
You
preventing it from going in a straight line?
The tether.
The tether, or the fact that I'm holding the tether. Okay? Were I to let this go, what would it do? It would fly off in a straight line, tangent to wherever I let it go. So if I let it go right here, it'll fly off over there and probably hit the board right behind Peyton's head. Okay? I won't do that because someone will get hurt. Okay? Someone will lose an eye and then it's a sport. It's no longer fun and games. Okay? So, what keeps something moving in a circle is a what? What's in this?
String.
No, it is a string. What's in it?
Tension.
Tension. Tension is a force. Okay? You don't get circular motion unless there is a force present to cause it. Okay? Even to do something as simple as turn a corner still requires a force. What force allows you to turn a corner?
Friction.
Friction. It's why you don't turn as well when it gets icy. Okay? There's less friction when it's icy, so you can't turn as well. Okay? Because the force that's supposed to keep you moving in a circle is smaller. So you either have to slow down or accept that you're going to follow Newton's first law and travel in a straight line, encountering whatever happens to be in a straight line from the point where you lost the corner. Okay? You guys all been in that situation before? Okay? What should you do in that situation?
Slow down.
Slow down and get off the brake and don't oversteer. What is your gut reaction? Pound the brake and oversteer, right? Like, oh, I'm not turning, so I'll crank the wheel harder and I'll hit the brakes even more. Okay, that's your gut reaction, but it is exactly the opposite of what you want to do. Okay, once your wheels are turned, okay, away from the direction you are traveling, like this, okay, if they're not rolling, you're not turning. Okay, that's the whole point of anti-lock brakes, is to keep your wheels turning so that you can steer while slowing down. You crank your wheels like this, and all they're doing is sliding along with them basically perpendicular to the direction you want to go. They're not doing anything at that point. Okay, and with you, meanwhile, slamming the brake through the floor, okay, it's also not giving the brakes a chance to back off and let those wheels start to turn again. Okay, you're relying on kinetic friction instead of static friction. Once you start to slide, it's all kinetic friction, and that's always smaller than static friction. Okay? So even though our gut reaction is to hit that pedal harder and crank that wheel farther, it is exactly the opposite of what you want to do. Okay? You want to steer into it a little bit to get yourself straightened and get off of the brake. Okay? Once you can get those wheels spinning again, then you can continue to make your turn. Most of us don't get the opportunity to think that through. Usually we've encountered something hard before we realize we should have done that. Okay? Does that make sense? Okay, so for something to move in a circle, there has to be a force that pulls it towards the middle. Okay, agreed? All right, so when I was just whirling this around in a horizontal circle, okay, the force that was keeping it in the circle was the string, okay, the tension in the string. Okay. If we're going around the corner, it's friction. The challenge with this unit is identifying what force is acting as what we call a centripetal force. Okay, one that makes you go towards the middle. Okay? All right, so this is what I was just doing. Sorry, Alex.
There's a difference between centrifugal and centripetal.
Well, I was actually just about to get to that, but I'll answer that. Okay, sometimes people, when I say centripetal, think I've mispronounced the word, because they're like, centripetal, it's supposed to be centrifugal. Okay, centrifugal force is not force. Okay, centrifugal means center fleeing. Centripetal means center seeking. The only reason that this tape went around and around in a circle was there was a force pulling it towards the middle, seeking the center. Okay, that sort of makes sense? I was always pulling towards the center. That's why it was always turning. Okay, so that's a centripetal force. A centrifugal force would be a force that would be trying to pull it directly out. In this situation, there isn't a force trying to pull the tape directly out of the circle. Were I to let it go, its inertia would cause it to go in a straight line. But that straight line is not straight out from the circle. It's tangent to wherever I let it go. Okay? So there's actually no centrifugal force in uniform circular motion. There's nothing trying to actively pull this thing in the opposite direction that I am. It feels like it, but that's just the object's inertia. So the force we often call centrifugal force or centripetal force is actually just the object's own inertia. It's the one that pastes you up against the window when your crazy driving friend takes a corner too fast. Okay? That's your inertia. You want to go in a straight line, but the door prevents it, and your seatbelt, hopefully. Okay? It's why you shouldn't go in one of those Jeeps or Broncos where the doors come off. Okay? I had a buddy who in high school had one of those, and one of my friends didn't wear a seatbelt, and he was fooling around the parking lot. Right out. Nothing to provide a centripetal force. Right out the door he went. Nice straight line, too. Okay? In fact, it's a good time to show you one of my favorite videos that I love to show. I call this video Motorcycles, Merry-Go-Rounds, and Morons. Okay? With good reason.